Okay, so hi everyone. So I'm happy to have you here for the second start session with me. For those who joined me the last time, I think we'll carry on the same approach. Whenever you have questions, please to drop them in the chat. So I'll answer them. I think feel free to interrupt me anyways. I think it's just not going to be a long session today. And thanks for your feedback on the previous session. That's very helpful. So I think we had mainly two main feedbacks on that. Like the first one is, I do agree with you guys when you say it could have been like 2 sessions instead of 1, just because like the content is quite dense, although I try to minimize really the amount of things that I want you to know about linear regression. And the other thing, I think I had another comment on the software use. I think you guys do not agree on the software that you want to use, which is really okay, just because I think people do use and have licenses for different things. So, I mean, it was like a tricky questions anyway that I have discussed with course directors at the beginning, is to really try and have some kind of survey and try to know what's the best software that you want guys to use. And I think from our survey was probably SPSS. Unfortunately, I don't have a license for SPSS. I do have for Stata, for like ours is open source, for SAS, but I just like the only one that I don't have a license for is SPSS. Anyways, the other thing is some of you really asked to have codes. Some others said it was a bit confusing to have codes when actually they don't know how to use them. So the idea was not really to teach you how to use the software or the or to code like the commands. It was more to see like how what kind of output are we expecting from the stats packages. And I think that's the main thing, just because whatever the software you're using, you end up having exactly the same output in your screen. So that's probably the main thing. We cannot teach stats without really knowing how to run stats. So I think that's why, like in all stats, like the last 20 years, probably we've been teaching stats with based on a software. And it's a way for you guys to distinguish between what's your input, what are the steps that you need to do, and what's the output that you would expect from the software. And I think it makes things less obscure and less vague when you know actually what are the things that you are going to get easily from a software, and what are the things that actually you need to think about and to enter into that software. So I think I'll carry on doing the same thing as before, but today I'm using Stata, so hopefully some of you are more familiar with Stata than with R. If you guys have any recommendation or any suggestion for us for the future, you can put them in the feedback and we can think of how to kind of introduce you to the software before kind of using it in the stats lecture. But it's really, really important to teach stats with the software. I cannot really teach without. Okay, so today is a logistic regression session. It's just an introduction. So what we want you to know today is to understand how to use and when to use logistic regression models, how to interpret the output when you run a logistic regression model. So I'm taking a binary exposure variable as an example. And the last thing that we want you to learn is how to assess the model fit using curves. Okay, so same old friend as before. So each time you see Jane, she's there to tell you important things in red boxes. Okay, so I think we have mainly 3 parts in this session. So I'm going to introduce logistic regression based on starting from the linear regression, just to see the link between the two. So logistic regression is known in the literature as a generalized linear model. So I think they all belong to the same family. The second point is to run logistic regression models in Stata and to see how we can interpret the output. I am just putting like few hints on how to adjust for confounders in this session, but I think it deserves like a whole session in itself. But hopefully we just like enlighten you about how important it is to adjust for confounders and what's the implication of that. The last bit is about using logistic regression as a classifier. This is like more a machine learning approach, so I'm not really going to kind of add a lot of details about this here. It's just because I think it's so important to understand that the logistic regression model is one of the very first machine learning techniques that have been used to classify observations. Okay. So this is a recap. I think you probably remember we use linear regression when we have a continuous output. We have used the linear regression to explain differences in blood pressure the last time. And we have considered different predictors, either age, sex, or BMI, different type of variables. And we could see that actually we could summarize the reality using a line. That's kind of a simplified form of describing the linear association between two variables. It's say, well, okay, so, sorry, they are linearly related, so I can fit a line that goes through the points, and then I can use that line to predict the SPP values, or to summarize the association in terms of slope and intercept. So I'm going to have another example today of linear regression. I'm going to try to see the relationship between the number of hours studying and the exam score based on a number of observations. It's like a hypothetical example, really. So this is the data that we have. So on the x-axis, you have like self-reported hours studying from 0 to 8. And on the y-axis, you have the exam score. Okay. So it's obviously a line. So according to my assumptions, I can run a linear regression model on this data. So on my linear regression model, what I'm going to get from the output from state or SPSS, two things: the intercept beta, where the line crosses the y-axis, and the beta one, which is the slope. Okay. So I did that, and this is our regression line. So regression line is given by a score. The intercept here is 16.4. If you look here at the point where the red line crosses the y-axis, is approximately 16. The slope now is 7.2, which means for 1 hour increase, 1 hour more studying, you would gain 7 points in score. So this is what it means. It means like that's the addition for 1 hour, for 1 unit increase in the number of hours you study, you will gain in 7.2 points in your score. Okay. So I want you guys in the chat to use this line to predict a score for someone who has spent 6 hours studying. Okay. So just like leave you a few seconds to try to use the red equation in order to estimate the exam score for 6 hours studying. Okay, so feel free to drop your answers in the chat. And even if you think you have the same answer as the people who answered before, I would like to see those answers so we can see if we reach a consistency in your responses. Okay, great. Thanks, guys. Okay. Yeah, I agree with you. It is about 60. So here I'm just like using the line. So for an x that is equal to 6, I'm going to project that on the y-axis, and it's approximately 60. So I can say if you study on average 6 hours, your estimated score is going to be 60. So you'll definitely pass this exam. Okay, so this is one of the uses of linear regression. This is prediction. So I'm using it to predict the score of my students. However, people often, they're not that interested in predicting individual scores. We are more interested in the overall association. So what you would see people reporting in the papers is the 7.2. That's the slope, that's the beta. So that's the main thing when we make an inference, saying, okay, I'm taking a sample of students and I'm trying to generalize that to the whole population, which is, for example, the university where I work, and say, okay, if a student work on average, I mean, if a student work 1 hour more, he is going definitely to gain 7 points in score. So this is the main results I'm going to report in my paper, if that was a paper. So these are like two distinct uses of regression models in general. So one is to make inference, to describe general associations, and one is to make predictions, and both are valid, of course. Okay. So now, if I am interested in seeing how can I describe, according to the number of hours spent studying, the probability for someone to pass the exam. So passing the exam, at least for stats in my module, is over 50. So you need to get over 50 marks to pass the exam. So as you can see, I used two different colors in order to distinguish between the group of people who passed and the group of people who didn't. And as you can see, there's some correlation in the, if you look at the two colors separately, you can see that those who did not pass are those actually who have spent less hours studying, and those who passed are those who spend more hours studying, which is what we would expect. Okay, so I'm going to rewrite this score above and below 50 as a binary variable. Okay, so this is a different plot. This is looking on the y-axis at the passing the exam, which is a binary variable, 0 for those who did not and 1 for those who did. And as you can see, these are the red points that I had before, and these are the blue points that I had before. So the red points are mainly for those who did not pass, and the blue ones are for those who passed. And as you can see, again, when the number of hours spent studying is below, say, 5, you would expect people to not pass the exam. Okay, so that's interesting to look at. If I had only a pass, 0 versus 1 binary variable, my question is, how could we model this relationship? Can I use the linear regression model in order to model that? I mean, technically I can, and that's why you can use any stats anywhere with any data, but it's not a good idea. You absolutely need to have some rationale for why you would use linear regression model in this case. So if I was ignoring the assumptions and the rationale, I'm going to get a line that actually crosses these two set of points. Now, is this a good model or not? Probably not, because I would expect to use a model in order, for example, to predict. However, if you try to use this line to predict, you can see you will end up having something below 0 and something above 1, which in our case does not make any sense, just because I want to predict 1 and 0. Or I can think of predicting a probability for someone to pass, which would be something between 1 and 0. So my model should not go beyond those cutoffs. Okay, so what would be best? Okay, I think I have a question. I think in this situation we use look. Yeah, I'm coming to that. Absolutely. Thanks, Oda. So I am moving now from my 0, 1 binary variable to a new outcome. And I think I prefer looking at the probability of passing the exam rather than just like only 2 points. Okay, so with my new outcome, there is the probability of passing the exam. As you can see, the risk is still constrained between 0 and 1, and all the probability will fall between these two models. Okay, so now the idea is, if I can find a function or a curve or whatever we can find to link the probability of someone who passes the exam to the number of hours studying, then I can use that model to make inference and I can use that model to predict. But it needs to be something that could fit the data and the structure of the data that I have. Okay, and also it needs to predict those with a number of hours studying that is low with a low probability, and those with a number of hours that is high with high probability. And as you can see, there's some kind of overlap here. So maybe there is a cutoff point where actually there will be an increase or a jump in the probability of passing an exam. That's probably because if you study more than 5 hours, which is probably adequate, then it probably depends on your prior knowledge or your skills or other things. So it just does not depend on the extra number of hours studying. So you better go to sleep rather than just like spending much more time studying, because it's important to sleep. Okay, so I think I'm going to try and fit something to this data. Okay, so this is like the function, one of the options. You might have so many options, but I'm not going through all the other options. One of the options that is interesting is this kind of S-shaped curve, which is actually nice. And for you medics, I think this could remind you of something like an association between toxicity and the dose response type of relationships. For example, if this was like levels of treatment and this was toxicity, you might expect, for example, when your level of treatment is near zero, there is no toxicity there, and then you might expect the toxicity to slowly increase at some point until it reaches a threshold. After that, it's going to jump, and then you will reach a plateau. So I think this kind of relationships are kind of real world relationships, and I think that's why we need to think of how the model fits these data, just because these data are real, and I need to understand the mechanism that actually is going to link the probability of my outcome to my predictor in order to decide what's the best model. I just cannot test all of them. So I have some prior knowledge of how this is kind of related. So that's why I think in this case, the S-shape association is going to fit well my data, just because I have some kind of two distinct areas here and there, and I have this increase in probabilities. Okay, so if we want to use this curve to predict the probability of passing for someone who spent 5 hours studying. So I'm not giving you an equation here, but I want you guys to look at the plot and try to really roughly approximate what would be the probability of passing the exam for someone who has spent 5 hours studying. Okay, it's definitely above 50. I think you all agree it's definitely, yeah, above 50. Okay, so thanks. Yeah, I think it's really like, just like with the, to visually try and see what's the, I think it's probably a quite high probability. And I would say if the 5 was here and I tried just to project that on the y-axis, I will be between 0, 8, and 1 probably. And here we go. So we are projecting the 5 on the curve and reading the probability on the y-axis. And we have 90% probability of passing the exam if we spend 5 hours studying. Okay, great. So I can build models and use them to predict the same way I did for linear regression. So, but what type of model is this? Okay, so another question is to now read on the y-axis 50% probability of passing and try to kind of see what's the minimum number of hours required for me to study in order to pass the exam. I think I won't let you guess, just because I think it's just not easy really to read on the plot. However, if I look here at 0.5 and then I project on the curve and then I look into the, on the x-axis is probably something near 5. Yeah. So what we can say to summarize the information that we get from this plot, one of the things I can say is you are required to study above 4.7 hours in order to get at least 50% chance of passing the exam. Okay, so now the difficult thing is this looks nice. However, I need an equation for this. So what's the equation for this, and how can I make the link with the linear model? So, okay. So the basic idea of going from linear regression to logistic regression is to make the outcome look similar to the one that we use in linear regression. So the outcome that we use in linear regression is a continuous outcome. It takes any value from minus infinity to plus infinity, any value. And in order for me to use the same structure of a linear model, I need to transform my y variable, which was 0, 1 variable of probability of passing the exam, to something that gets value from minus infinity to plus infinity. I definitely need a continuous outcome here. Okay, so this is the link between, this is something that is going to lead to logistic regression, to linear regression, sorry, from this logistic regression thing. However, instead, there's so many other ways to deal with this. This is one of the ways, which is the logistic regression model, which is part of the linear family model. Okay, so now I need my link function. I'm going to try and think, what are the options that I have? Okay, so the first natural thing is, instead of using a 0, 1 binary variable, I'm going to try and predict a probability. So from here till the end, my y is going to mean a probability. So y is probability of passing the exam. Okay, y is constrained by 0, 1. It could not be used in a linear regression model as a dependent variable. It needs to have values, negative and positive values. So there's something in stats, and I think you probably came across this before, which is like called the odds of y. So the odds of y is the probability of y equal to 1 divided by probability of y equal to 0. So this odds thing, we are going to have examples of how to calculate the odds. However, the idea with the odds, it doesn't take negative values. So that could be one of the transformation, one of the steps that I'm going to use. So I have this nice idea of using the odds of y, just like to allow me to have a scale of values that is more comprehensive than just like the 0, 1. So I'm approaching a little bit to kind of a continuous form. However, I'm still not there. So what could transform the odds of y that takes value from 0 to plus infinity to something that takes values from minus infinity to plus infinity? Anyways, I think this is probably something that you have learned a long time ago, probably at school, which is the log function. You just log the odds, and log takes only positive values, and the output is going to be any value from minus infinity to plus infinity. Okay, so I think you guys don't really need to remember all these steps. The idea is starting from a binary variable in order to be able to use this outcome in linear regression model. I'm going to transform it. And the way I choose to transform it, there's so many other ways. One of the ways is to use the log odds of y. And we'll see how to calculate the log odds of y. So this is called a logit function. So this is a link between the probability and the odds. Okay, so now as a summary, I have on the left my linear regression model, my line that doesn't fit the data well, and I have on the right, my logistic regression model with this S-curve. So the logistic model, or the logistic function, is going to link the probabilities here to my predictor X. Okay, in the same way it does that, mathematically it's very equivalent as well to linking the log odds to the X predictor. So I think, yeah, so this is what I'm saying here. I'm not going to demonstrate that, it's just like an equation that I can write. And if you have any questions on that later, I can try and explain. However, starting from my transformation here, and assuming that the log odds are linearly related to my predictor, I can end up having a link between the log odds and my predictor. And I can use then a line, just because the log odds takes any values. Okay, so what I want you to remember is just making that transformation will make me have a smooth change in risk throughout the range of X. So that's like the S-curve, I think. So what I want to model is something that increases slowly up to some threshold and then reaches a plateau, which again is the S-curve. So this shape is consistent with maybe dose-response relationships, and we're going to see an example just in the next section. Okay, so my logistic regression model, I'm going to use data. I think it's probably available in Stata, or I think it's easy to download. So this is linking an outcome, which is ischemic heart disease, to whether people have or have not high cholesterol levels. So my outcome is going to be IHG, and my exposure is going to be cholesterol levels. So I'm going to try to see the link between the two. How can I model the link between the two? So just like I have put a description here on the study design, so it's a nested case control studies. So this is a more NEPI term, which means that after they have run their prospective study, they took all the cases in that study and matched them with some controls. And then we have a case control study. Okay, so this is the output from Stata when I try to tabulate the IHG outcome with the high versus low level of cholesterol. Okay, so I want you guys to first calculate the proportions. So we're going to just like answer the first question. Can you try and calculate the proportions with IHG in those with and without high cholesterol from this table? So you need to look separately at those without high cholesterol and see what's the proportion with IHG, and then look at those with high cholesterol and see what's the proportion of IHG. Yeah, great. Proportion. Okay. Yeah, thanks, guys. Absolutely. So the proportion without would be like the 24 here, cases divided by the total, 97, and the proportion with is going to be 44 divided by 109. Okay, so I'm going to see the numbers. Yeah, so you're going to have the 24 divided by the total is going to give you 0.25. And the proportion with IHG amongst those with high cholesterol level is going to be 0.4. Okay, so it's easier to calculate proportions. So now what about the odds? So what about that's my second question. So if you can just like put the numbers in the chat, what about the odds for IHG in those with low cholesterol levels and the odds of IHG in those with high cholesterol levels? So the notion of proportion of odds is a bit different from that of proportions, but I guess you probably know that. So if you can just put some numbers for the odds. Hope you didn't see it. So I'm trying to answer the second point, guys. Okay, so here's the table and here's the question. Calculate the odds of IHG in those with and without high cholesterol. Okay, just to help you with this, the odds is going to compare. For example, when I talk about the odds in those with low cholesterol, I need to compare basically the cases to the controls in that group. So I want to see how does the cases compare to the control in that group. Yeah, great. Yeah, these are the odds. The odds are actually, so the odds in those with low cholesterol is going to compare cases to controls in the low cholesterol group, and the odds in the high is going to control cases to controls. So the calculation is given by this. Okay, so my odds for IHG in those with high cholesterol is going to be 44 divided by 65. This is comparing cases to controls. And the odds in those with low cholesterol levels for IHG is going to compare cases to controls. Okay, so I get these two numbers, and I think I've seen the correct numbers in the chat. So now a very nice and easy to interpret measure would be to just like divide these two odds, and then have an odds ratio. So this is what we call an odds ratio. So this is comparing the odds of the disease in the exposed to the odds of the disease in the unexposed. So I'm just going to take these two numbers. My odds of the disease in the exposed is going to be 0.68, and the odds of the disease in the unexposed is going to be 0.33. So it's actually comparing how many times the exposed are going to get the disease as compared to the unexposed. So there's a number here that is 2.06. So there is twice as many risk or odds for those who are unexposed to get the disease as those who are exposed. Okay, so we talk about twofold increase in odds in those who are exposed as compared to those who are unexposed. So this is one of the measures of association that you probably came across in epidemiology. And the idea for a logistic regression model is trying to model that odds ratio. So how can we get an odds ratio from Stata? Or how can we get the odds ratio from the 2 by 2 table? I think you know how to get that. So let's look at our logistic regression model here. So my logistic regression model is based on the idea that I'm going to look at the log odds of the outcome, just because it's a continuous variable, as we have explained in the first section. So just because it's a continuous variable, I'm assuming it has some linear relationship with my exposure. And I'm going to use exactly the same equation as we did in linear regression. We just have two things to estimate, a beta 0 and a beta 1. Intercept and slope, same as before. It's just like the outcome that it looks a bit different. Okay, so now in order for me to understand what's beta 0 and beta 1 in logistic regression, just to remind you guys, in linear regression, my beta 0 was the intercept. For a binary variable, it was like the mean in the reference group. And the beta 1 in linear regression was the slope. That was like the increase in the outcome per 1 unit increase in the exposure if it was continuous. And if it was a binary exposure, it was like the difference in mean between the two groups. Anyways, this is just like to remind you very briefly. So now I need to know what's my beta 0 and what's my beta 1. In order to get beta 0, in this equation, I need to replace the high cholesterol by 0. So if I take someone with low cholesterol level, so their value is going to be 0. Someone with low cholesterol value would have 0 for high cholesterol, and someone with high cholesterol value would have 1 for high cholesterol. Okay, so in my equation here, I'm just going to look at the participant who has a low cholesterol level. So his high cholesterol variable is going to be 0. So if I put 0 here times the beta 1 is going to disappear, right? So my equation is going to be log odds of IHG is equal to beta 0. So just to remind myself, I'm looking at those who are unexposed here because I have replaced a high cholesterol level by 0. Which means that I'm looking at someone who is unexposed, okay? And I get the beta 0, which means that the beta 0 is the log odds in the unexposed, okay? Replacing the high cholesterol level by 0 means I'm looking at those who are unexposed, because those who are exposed take value 1, okay? Then it leads in my equation to log odds of IHG in those who are unexposed is equal to beta 0. Now, is it important? Is it not? Intercept, same as before, is not that important. Okay, so what is important for me to report is the beta 1, who is going to describe the overall association. So let's see how we're going to get the beta 1. Okay, so this is my equation. And now I'm going to look at those who are exposed, right? So I'm going to replace the high cholesterol value with 1. Now I'm looking at those who are exposed. Okay, so if I replace my high cholesterol value with 1, my log odds is going to be equal to beta 0 plus beta 1. What does that mean? That's not that straightforward to understand. Okay, so I'm just going to isolate this beta 1 and try to see what this is going to lead me to. So beta 1 from this equation is going to be the log odds minus beta 0. So that's the log odds in the exposed minus the beta 0, which was the log odds in the unexposed. Okay, this is my second line. My third line, okay, so there is an error here, guys. Sorry, I'm going to correct that. There is no log here. I'm going to correct that and edit the slides. Sorry. So moving from line 2 to line 3, is just like a relationship that you probably learned a long time ago about the logs, the log function. So log A minus log B is log A divided by B. Okay, so this is log odds in the exposed divided by odds in the unexposed. So please ignore the second log here, just it's a typo. Okay, so finally, my beta 1 is nothing more than the log odds ratio. That's great, which means that I can run a logistic regression model in Stata or in any software that you use. Look at the beta 1. This is going to be my log odds ratio. I can exponentiate it and get the odds ratio and job done. Okay, so let's look at our previous example. In my previous example, you have, guys, hand calculated the odds in the unexposed. It was something about 0.33, and we have hand calculated the odds ratio, which was 2.06. So if I take these two values now and plug them in the equation, my equation is going to give me log odds of IHD is going to be beta 0, which is the odds in the unexposed, the log odds in the unexposed. So I need to log the 0.33. And then the beta 1, we said it was like the log odds ratio. So I need to log the 2.06. What does this mean? It means that in a 2x2 table, if you have a binary outcome and a binary exposure, you can just hand calculate the odds ratio. You don't need a logistic regression model to run in order to get that. That's easy to do. You just can do it by hand. Or if you don't want to struggle, what you can do is to run a logistic regression model in the software. So this is how it works in Stata. So I have my logistic function and I have my outcome. I need to put the outcome first, and I have my binary exposure, which I need to put second. So then I have a table with the output, and this table is very similar to any sort of table that you get from a stats package when you run a logistic regression model. Okay, so what the output is giving me are numbers that I'm quite familiar with, just because I just got them by hand. When I just calculated this by hand, I just got them. So it's exactly the same as before. So now what does this mean? Just to remind ourselves, we said that the beta 1, which is the coefficient for high cholesterol value, means it's the log odds ratio. That's the log odds ratio. So I can take this and exponentiate it and get the odds ratio. The constant, I can just pretty much ignore it just because I don't need it, but just to remind myself, it was the log odds in the unexposed, but that's not important. Now, what I can do is take this high cholesterol coefficient and just exponentiate it. If you exponentiate this in a calculator, guys, you're going to have 2.06. Or you can ask Stata to output odds ratio instead of log odds ratio, because you have two options. There are some advantages of using the log scale and some other advantages of using the exponentiated scale. So I'm just going to use the odds ratio output here, just because I think it makes more sense for you guys. And there's so many other scenarios where I will need to look at the log odds ratio. And I have only one example of this coming later. Okay, so fine. What do I need to remember? I need to remember is that the logistic regression model using a binary outcome and a binary exposure is equivalent to a 2x2 table where I can calculate the odds ratio by hand. So I get an odds ratio which is exactly equal to the one that I got by hand. So now, how to interpret this odds ratio? The interpretation of an odds ratio is to say there is a twofold increase in odds in the exposed group as compared to the unexposed. In this example, there's twofold increase in the odds of IHD in those with high blood pressure, with high cholesterol level, as compared to those with low cholesterol level. So this is how I interpret the result, and this is how most of the papers using a logistic regression would probably interpret the results as well, as twofold increase, one-fold increase, or 0.5-fold increase, etc. Okay, so now, if you remember, we have looked at other things in the output. We have looked at standard errors. We have looked at p-values. I'm not going to go through this here in this session. I think you probably remember what we did in linear regression. The main thing is to report a p-value to say whether this result is significantly different from 0 or not, which is the case. My p-value is below 0.05. And the other thing I need to report is what kind of uncertainty I have around my estimate. I cannot be 100% sure that this is the right estimate in the population, so I need to report a confidence interval. So if you want to construct a very nice and smooth sentence in a paper, you need to say there is X-fold increase in the odds of the outcome for those who are exposed as compared to those who are unexposed, and in brackets you would put the odds ratio, confidence intervals, and p-value. You need the three things in order to have like the description of the overall association. So what I'm doing here, I'm doing inference. This is what we call doing inference, which means that I'm taking my sample, getting odds ratio, trying to have some kind of general conclusion on what's going on in my population and saying there's twofold increase in odds. In some papers, you will see people talking about twofold increase in risk rather than odds when actually they are using odds ratio. Sometimes it's fine. Sometimes it's fine. Sometimes it's fine to say that when actually your outcome is rare, odds ratios and risk ratios are very similar. This is, again, an think. So anyways, but what I recommend is to use the sentence as it is here to say there is x-fold increase in odds for those who are exposed as compared to those who are unexposed. Okay, so this is a summary of my logistic regression model. So in my logistic regression model, I have a linear link between the log odds and my predictor. My beta 0, which is I can absolutely ignore, is the log odds in the unexposed, and sometimes it does not make sense. As we saw in linear regression, sometimes the intercept doesn't make sense. The beta 1 is what I need to report, which is the log odds ratio. I can report it in terms of odds ratio by exponentiating the beta 1, or just like asking the software to do that for me. Okay, so why do we do this? We do this in order to make some kind of inference about our association, and we use always a statistical package. We are never going to do that by hand. And the advantage of using regression, the same as what we said in linear regression, is to be able to adjust for other confounders. And I'm going to show you an example of this. So I'm not going to deal with 2x2 tables all the time. I'm going to want to adjust for age, sex, smoking, BMI, other factors in my model, and that's why I'm using logistic regression. So the estimation method here is called maximum likelihood. I won't have time to go through this, but you don't really need to know in order to be able to run and interpret the output from logistic regression. If you have any further question on this, I can answer them later. Okay, so some kind of link with epidemiology. When is it correct to use a logistic regression? It's correct to use logistic regression whenever odds ratio makes sense. Whenever odds ratio makes sense, you can use it. So you can use that in a cross-sectional study and do exactly the same as before, and you can use that in unmatched case control study. Just so I have put something in the appendices about the matched case control studies. When you have matching by age or matching by other factors, this is not called, this is not a general logistic regression. This is what is called a conditional logistic regression, which is different from the unconditional logistic regression. Anyways, what I'm talking about here is called the unconditional logistic regression, which is like the most widely used conditional regression form. There are other forms. I have put some hints in the appendices for those who wonder how do we deal with matching in case control studies. Anyway, there was like just like in an epi hint, just like to say that odds ratio can probably be used anytime. I mean, it just like you need to be careful about how to interpret the odds ratio in terms of odds or in terms of risk. Okay, so this is just a slide on the confounding by age. So here in my first model, I'm looking at the association between IHG and high cholesterol, okay? And this is my odds ratio, which was like 2.06. Same as before. Now, what's the implication of age? You might expect people will have different odds or different risks for to develop or to get an IHG according to their age. Age is so important in cardiovascular diseases that you absolutely need to adjust for it. And sex the same way. But I think in my data set, I have only males, so that's why I didn't adjust for sex. So what confounding means? Confounding could distort the association. So you might like think that the association is only due to high cholesterol, that there is twofold increase in odds only due to high cholesterol. It's not that clear. What's the distribution of age in those who are exposed, in those who are exposed? Maybe you can have like some part of the association that is explained by age, which means that those with high cholesterol level may tend to have older age than those with low cholesterol level. That's an effect of confounding by age. So if I want to eliminate or like isolate the effect of age, I can just like put age in the model. And what I need to look at is the change in the odds ratio before and after I do that. So before I did that, there were twofold increase. After I did that, there was like 1.9 fold increase. So it alters my odds ratio, which means that my association is less strong than before, which what you would expect when you actually include age in your model. So the effect of confounding could be like to increase association, to decrease association, or not to do anything to an association. And in that case, it's not a confounder. So age here is definitely a confounder. So I need only to focus on the beta or the association linking high cholesterol to my outcome. I'm not here to interpret the effect that age has on the risk of IHD. That's not my purpose. My purpose is to concentrate on my overall association between high cholesterol and IHD and how is that affected by age. Okay, so would you say that actually the decrease in odds ratio from 2 to 1.9 is big or not big? That's very debatable. That's, I think, something people hardly agree on, just because, I mean, you need to think, I mean, to which extent a decrease is an important decrease or an increase an important decrease, an increase. So what we can do is compare these two odds ratio, and I think a lot of people do this in epidemiology. We do less of these things in stats, so we have other ways, but one of the most common way is to go back to the log scale, because everything has been estimated on the log scale, and an odds ratio is just like an exponentiation of that log odds ratio. So if in order to compare, I absolutely need to go back to the log scale. So now, what does that mean? I'm going to compare the coefficient before to the coefficient after and see how much decrease I had in my coefficient. So this is simply done using this simple equation, which is like looking at the difference and how much of that difference is as compared to what I had before. So if I do the subtraction between the new, the old unadjusted beta to the new adjusted beta and divided by the old one, I'm going to get about 12%, which means there is approximately 10% decrease in my association after adjusting for the confounder. So if you really need a way to interpret confounding, this is one of the ways, and this is more a nappy way to compare the impact of confounder on the association. But I think you probably have a lot of stuff to put in a paper, then actually we don't really report increases or decreases in association. We just say that after adjusting for age, sex, smoking, BMI, blah, 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 I have a 1.9 increase in odds of my IHD that is due to high cholesterol levels. Okay, so the idea is at least to appreciate that once you adjust for other confounders, your association could decrease, increase, or stay the same. This is the only thing that I wanted to say about confounding, so you don't have like regression sessions without something on confounding. So my last bit, which is just like an insight of how do people use logistic in machine learning. I think it's probably there's a lot of talks about this, so just like it's only a summary of what you can get from data in order to give you a hint about how well the model is performing. So the idea is I can run my logistic regression model, taking IHG as the outcome and taking this high cholesterol and age in my model as predictors. This is a model that could like make some sort of predictions. Then how good, how bad the prediction is, I can output in data what is called a confusion matrix. You can do this in any software. This is going to tell you what are the pairs that has been classified correctly and what are the pairs that has been misclassified, which means that, so how does that work? I'm going to get probabilities of for IHD, right? I'm going to get probability of 0.6. Okay, so I have a probability of 0.6 for someone. Then I can just like set a threshold. I can just decide arbitrary threshold of 0.5 and say, if I have probability that exceeds 50%, 0.5, I'm going to classify this person as having the disease. Okay, and then if I get the probability that is low than 0.5, I'm going to classify that person as not having the disease. Okay, so this is my classification. I'm going to do blinded to the true values. And then I'm going to contrast that to the true values and say how much pairs or how much people I'm just like classified correctly and how much people I misclassified. Okay, comparing the prediction to the true observations. Okay, so what are the pairs that has been correctly classified here? So those who had the disease, 14 of those who had the disease have been classified as having the disease. And 128 of those who did not have the disease has been classified as not having the disease. So my errors here in my confusion matrix are the 10 and the 54 and 54. This has been misclassified. There is no correct matching between the expectation and between the true value. Okay, so one of the ways to assess how correctly my classifier is going to classify my observation is just like to have a sort of ratio. A ratio between the pairs that have been correctly classified as having the disease and not having the disease, divided by the total number of pairs, which means that I'm just going to do this. So this is just like explaining how you would do it. So we need to set a cutoff. So I have decided of 0.5, Stata did the same. So this is my cutoff of 0.5, which means I'm just calculating prediction, comparing it to 0.5 and classifying people. There might be so many other thresholds. It depends on what you want to decide. And then I'm going to check the prediction against the actual outcome. And here we go. So those who have been classified correctly represent 70% of the total number of pairs. 70%. How did they get that? The 70% that is here in the output is coming from this diagonal of the correctly classified people. So I have 14 here that has been classified correctly, and 128 have been classified correctly. So I'm going just to sum that and divide it by the total number of people, which is 206. Okay, so what I'm going to have is like the proportion of people that have been classified correctly as compared to the whole sample, which is approximately 70%. It's not too bad, but this is using a cutoff of 0.5. You might want to use another cutoff, which means, for example, say, I don't know, if you want to, you can be more strict than 0.5 and you can be less strict than 0.5. If you want to get absolutely all those having the disease, then you probably want to lower your threshold. Say for Ebola, for example, if you want to detect all those with Ebola in order to avoid an outbreak, you're going to set your threshold to 0.1. You don't want to miss the true positives. You want to have all of them. So you want to lower your threshold to 0.1, which means if I have a probability that it is above 0.1, I'm going to consider that person as having Ebola. Yeah, it's very generous as a threshold, but is it the right choice? It's not. It depends on the purpose. It depends on the rationale why you're using this. So if, as I said, if you want to avoid an outbreak, you probably want to detect all true positives. You can detect all those with the disease. So you probably want to lower that threshold. Now you can decide to be more strict and having a higher threshold than 0.5. You want to only treat those with you want your test to be specific, so you can decide on a threshold of 0.9. The problem in doing that is you're going to miss true positives as well. So I think there's a kind of compromise between the false and the true positive that you need to have. So hopefully this is summarized using what is known as the ROC curve. So the ROC curves are going to put the false positives on the x-axis and the true positive on the y-axis, and it's going to compare the two using different cutoffs. So it's not only 0.5 cutoffs here, I'm screening all sort of cutoffs, and this is a way for us to assess how good is our model. So the straight line here on the diagonal means that this is a classifier that is not able to distinguish between those who have the disease and those who have not the disease. So this is what you want to avoid. You want your curve to be as far from this line as possible. So the further from the line is, the better your classifier is. So there is a value that people use to assess the performance of classifiers, which is the area under the curve. Because as I said, the farthest you are from this line, the better it is. So if you have a curve that is going like this, it's better than to have a curve that is near from the diagonal. So this is what is known as area under the curve, the IUC. number. So this is something that you get from Stata. You don't need to do any hand calculation for this. So the area under the curve is 70% here. What does that mean? This is only meaningful when you want to compare your classifier to other type of classifiers. A classifier could be a score. That could be like any kind of a cardiovascular disease score, or it depends on what's the type of your outcome. So you can decide and say, I'm going to build a score using like the predictor that I think are going to explain IHD. And you can publish that and say, my score is very good just because it outperforms the scores out there in the literature. How can you say that? You can only say that if you contrast some measure of model fit of your model to measure of model fit of the model that are published. So one of the ways to make that comparison between the model performances is to look at the area under the curve. That's one of the ways. So, I mean, of course, you will reach like the best performance ever if you reach 1, which is like the total area of the square here, if your curves go up to the 1 that is here. Anyways, so this was just like a hint. It's so easy to get from Stata these things that it's actually good to have a look at them. Now, the machine learning side of things is really much more complex than that. So when people do this classification thing, they use 3 distinct data sets. They don't use the whole data set in order to kind of build the model and then test the model and assess the model fit. This is not how we do, just because we are biased. If we use the same data, to get the estimate and then say, okay, how good is going to classify my people? I mean, you just build your model using your data. So of course your model is going to be good in classifying your own data. So what you want to do is to use one data set to build the model, to get the estimates, to get the score, and then use a different data set in order to tweak the estimate and make them better, and use a third data set in order to test the performance of your final model. So this is how we usually do in machine learning. We don't use one whole data set to do that. We just like split the available data, whereas it's like the actual data or supplementary data, and then make this kind of different steps in order to get to a final model and assess the accuracy of the final model. Anyway, this was just like a hint. That's really important to really always remember that logistic regression is one of the very first machine learning technique used as a classifier, which is great actually, just because it's very simple as compared to much more sophisticated methods that people might use. Anyway, sorry for overrunning. So I think by now, hopefully you understand when to use logistic regression model. Of course, when you have a binary outcome, how to run a logistic regression model and get the estimate. This is using a statistical software. The main thing is to know what's the information that I need to extract from the output in order to describe the overall association. If you want to do more like a prediction work, then you need to do this to look at the area under the curve and report the performance of your model. Okay, thank you very much. I'm happy to take any questions, I think, yeah, in the next 3 minutes. What if I have 3 outcomes? Okay, yeah. So then you will use multi-level models. I mean, it's actually kind of the same thing as these family of models that I'm just like introducing. However, it's not. You cannot use the logistic regression that takes binary outcomes, just like the. So it's called ordinal logistic regression if you want to Google that. So it takes an outcome with like different levels. And like all the models actually basically can be extended to different levels. About the confounding effect and the odds of unexposed, how can we report them in words? Okay, so for the confounding effect, the way we report it, we don't report the confounding effect itself. We just say the association was attenuated after adjusting for age. And I just report the odds ratio before and after, and this is what we do in papers. Sometimes we show sequential adjustment, try to describe what's the confounder that has the stronger effect on my association. And I'm always concentrating on my main exposure and my outcome. So I always like add a sentence in the text saying, after adjusting for this and that, my association was attenuated, which means that I'm reducing residual confounding, which is a good thing that reviewers are looking for. So they want you to say, I have dealt with residual confounding. My association is not biased, is not very biased just because I could incorporate as many confounders as I have in my data set. And you'll always like be very limited with the, limited by, constrained by the number of variables that you have. You might want to adjust for something that you don't have in your data set. So it's not like a 100%, it's not like really that easy to say that we eliminated residual confounding. What we are hoping for is like to minimize the effect of residual confounding. Okay, can a confounder increase the association? And what would that mean? Yes, absolutely. You can adjust for confounders and see that the association is increasing. That's called negative confounder. It's because it's interacting with something else in the model. Say, for example, if you're looking at sodium and potassium, for example, and association with CVD or SPP, whatever. So you might expect sodium to have a negative effect and potassium to have a positive effect. Both correlate with each other. So if you add potassium to your model, it's going to increase the apparent effect of the sodium. So this is called negative confounding. If you want to Google that, it's like an epi concept that is called negative confounding that might lead to an increase in the association, but it's much more complicated than that. Okay, I can use the odds ratio in meta-analysis. If I have a number of events for each group in a study, I should convert it to the odds ratio, then use. Absolutely, you can. There's no problem with that. You can. I think you will probably want to go for the best choice of the measure of association. I think you'll see next week Cox models and survival models. If you think the information about the time or the time that people has spent being exposed to some sort of exposure is important, or if like the baseline hazard of your the observation in your data set is important, then you'll go for like time to event type of analysis. So I think, yes, you can use odds ratio whenever you think odds ratio is a relevant measure of association. If you have, for example, in case control studies will be really widely used. For if you have a time to event data, you might use Cox, for example. But anyways, whatever you use, if it's like a cohort study, you end up having a very similar results between the odds ratio and the risk and the relative risk. As I said, if your event is not is rare. Okay, regarding the ROC curve, can you please explain again what cutoffs mean? Yeah, so the cutoff is used for classification. Yeah, the cutoff is used for classification. As I said, I built my logistic model and I get probabilities. And now I look at one participant who has probability of 0.7. So this person has 70% of having the disease. Now, 70%, is it a high probability or is it a low probability? Should I say this person is very likely to have the disease or not? This is very arbitrary, okay? So I decided, and Stata decided to use a cutoff of 0.5, I think because everyone is happy with that. I would say 0.7% or 70% of getting the disease is more than 50%. So I would probably classify this person as likely to have the disease. So that's one threshold. The other choices that I might have, as I mentioned, like the example with Ebola, if I want to treat people having Ebola, I think I will probably set that threshold to something lower than 0.5. I'll probably set it to 0.1. What does that mean? If a participant, I calculate the probability for this participant and his probability is 0.2, should I classify this as having Ebola or not? I think because I want to avoid an outbreak, then probably yes. I'm going to see whether I'm going to treat him or not. I'm going to consider that case as having the disease. So that threshold thing, so very often is like the alpha at the significant level. Everyone is happy with 0.05 and just people don't question that. 95% confidence intervals, people don't question that. The 0.5 for the classifier, usually people don't question that. Unless you really want to kind of go to the performance of this of your model and show like that actually it depends on different, like you screen all the thresholds available and get one summary value, which is the area under the curve. I think that's probably very helpful. But anyways, that cutoff depends really on your question. It just does not depend on the model. It just like depends on the real data. Okay. Okay, guys. So I think we'll probably stop here. I'm going to. I'm going to correct that typo in my slides and send it back to Lisha. And then I think we're going to upload the slides on the website. So if you think it's very long to hear the recording, then you just can use the slides if you want to replicate my codes, and please do. If you need any more kind of stat courses, I think you probably need to put that in the feedback. And also, if you think that you don't know how to use the software, and that's probably something we probably can think about in the future, then please do put that in the feedback form. So what else can I say? So yeah, this was like just like an introduction. I was really very happy to kind of have these two sessions with you guys. You will see Cox is very interesting. Survival analysis are very interesting, and they're like, I think, the most commonly used kind of type of analysis in trials. So I think looking forward for the next session. I hope you will enjoy it, guys. And I think I'll probably leave you here.